we talked about straight line motion. We looked at projectile motion, which is when we said, okay, well, it's not a straight line. We can break it up into its components. The reality is there's only one other type of motion. Either we're going to move in a straight line or we're going to move in a circle. So before we look at circular motion in a great amount of detail, just need to define a few things. So angular velocity. So there's the circle that we're going to be travelling in, and obviously it has a radius, and we're travelling around the point O. Now, as it moves, it will sweep out some angle, theta. Angular velocity is simply the rate of change of that angle. So if you like, you could think of the angle changing being an angular displacement. So instead of the length changing, it's the angle changing. So it's the rate of change of theta with respect to time. Notice we measure it in radians per second. So we're always using radians for this. Omega is a symbol that's commonly used for angular velocity. But of course, because it is a rate of change of theta, we could write it as d theta to t. And also because we're talking about motion, we could use the dot notation and just call it theta dot. Now, linear velocity, I mean, that's terrific if we know how quick we're going around the circle. But if we want to know our actual velocity or our speed, then it's the linear velocity that we want if we were moving in a straight line. It's also known as tangential velocity because it's simply the tangent at that point. So at any particular point in the circle, we could draw a tangent. And if we were thinking about the vectors, that would be the angle we'd be going off. Now, if it was at the bottom of the circle, brilliant, it'd be horizontal motion. If it was at the side of the circle, it'd be vertical motion. But somewhere in between, again, we might use vectors to actually calculate things out. But it'll be the tangent. So there it is, at some point, just like projectile motion, really. Imagine it's going off at some angle with a velocity. Now let's work it out. The arc AP, I'm going to call x. So the distance we travel around the circle, I'm going to call x. Now we know x is equal to r theta. So therefore, if I differentiate both sides, and remembering radius is a constant, dx to t is the radius times d theta to t. With d theta to t we just called omega. And so there's our conversion. Because dx to t is of course our linear velocity. So velocity, or linear velocity, will always be the radius times the angular velocity. Just like the length of the arc was always the radius times the angle. So the period, very similar to what we've seen before, it'll always be 2 pi over that angular velocity. So that's the time it takes for one revolution to go around the circle completely. All right, let's look at just a simple example. So we have a satellite circling around the Earth, and it does 20 revolutions in a day. So we want to know, how fast is that going? What's that actually in radians per second, not revolutions per day? Well, I convert it to radians. Now, one revolution is 2 pi radians. So I know it'll do 20 times 2 pi radians in a day. I want to know how many it does in a second. So if I divide that by 24 for hours, and then 60 for minutes, and another 60 to get it down to seconds, we come up with pi on 2,160 radians per second. So how fast is that satellite actually going? If the radius is 9,000 kilometres, so our satellite is 9,000 kilometres from the centre of the Earth, how fast is it going in kilometres per hour? To get some sort of sense of that. So well, velocity is radius times omega. So 9,000 times pi on 2,160. That's kilometres per second. Multiply it by 60 for minutes, multiply it by 60, and we get kilometres per hour. And in fact, those satellites are moving pretty quick. 15,000 pi kilometres per hour. So I suppose technically, if the satellite was travelling over, or let's say the Great Western Highway, which has got a speed limit of, what's it got, about 80 for the Great Western Highway? 80 kilometres per hour, I think they'd get a very big fine. because that's considerably more than 80 kilometres per hour. All right, that is Patel. But that's all I really want to talk about, just as a start for circular motion, and then we can look at it in more detail after you've had your camp and you're all refreshed.